This video is a discussion of the definite integral and the properties that go with it. This is a direct follow-up to the Riemann sum videos. The definite integral starts with the premise that f is a continuous function on the closed interval a to b. This is always, whenever we talk about integration, we always start with the phrase that f must be continuous because that is a requirement for integrability. The definite integral of f with respect to x is denoted in a very similar way to the indefinite integral with that elongated s that is the integration symbol. But now we're going to have a subscript of a and a superscript of b. These correspond to the endpoints of the interval. They are called the limits of integration. Aside from those, the rest of the notation is the same for the indefinite integral as it is here. So we just added those limits of integration. Now, the definite integral is defined as the net area of the region bound by the graph of f and the x-axis on the interval from a to b. This is a familiar, or should be a familiar statement from the Riemann sum lesson. It's actually exactly what the Riemann sum is. The definite integral from a to b of f of x dx is equal to the limit as n approaches infinity of the sum from 1 to n of f of x sub I times delta x. Now that can be a left endpoint, a right endpoint, a midpoint, etc. But to be consistent here, we'll stick with the right endpoint Riemann sum formulas. Delta x is equal to b minus a over n. And x sub I is equal to a plus I times delta x. Those are the formulas that define the right endpoint Riemann sum. So what this means is that we have a much more compact way to write the long phrase, find the area of the region bound by the graph of f of x equals whatever and the x-axis on the interval a to b. We have a much more compact way to write that. Now we can simply write the definite integral. For example, now nothing about the calculations has changed, but for example, evaluate the definite integral from -1 to 3 of negative x squared plus 9 dx. So this is still the Riemann sum. We still have to do that. It's just a much more compact way of writing. Find the area of the region bound by the graph of, etc. So we still need to be able to identify all the pieces. So from this, we have that our function is negative x squared plus 9, and our interval is from -1 to 3. The rest of this is still the same. So to set up our Riemann sum, we start with delta x equals b minus a over n, where b is 3, a is -1, and n is unspecified, so that our delta x is 4 over n. From that, we can then fill in our formula for x sub I, which is a plus I times delta x, where a is -1, and delta x is the 4 over n we just calculated. Now, rather than just attempt to do the limit and the sum and the composition f of x sub I all at once, I like to break those down piecemeal. So we're going to do the f of x sub I and simplify that composition so that when we get to the sum, it's already in its simplest form. Negative 1, oh, excuse me, I forgot the negative sign in front of the whole thing. Negative x squared, where this is our input formula, plus 9. We will, of course, need to expand this, which is not as simple as just multiplying each of the, or I'm sorry, squaring each of the terms. That actually has to be FOILed out, if you will. I will leave that for you to do if you want to pause the video and work that through very quickly. Now, we will need to distribute the negative in front of the parentheses before we combine the like terms, but the only terms to combine will be the constant terms. And they combine to give us 8. We can now put this into our summation formula. So we have the sum from I equals 1 to n of 8 plus 8 over n I minus 16 over n squared I squared times delta x. We'll need to distribute the 4 over n. Which gives us 32 over n plus 32 over n squared I. Be careful about the exponents on those n's in the denominator. It's very easy to forget the exponent or forget to multiply the n in the bottom of 8 over n times the n in the bottom of 4 over n. The same thing for the third term. 16 times 4 is 64 over n cubed times I squared. And at this point, we're ready to apply our properties and formulas of summation. So each term can be summed separately. One of the important things to realize here is that in the summation, I is the variable. N is an unspecified constant. So anything that contains an n, but not an I, is a constant. So this first term, 32 over n, this is constant. So our formula for the sum of a constant is that constant times n. In the second term, the 32 over n squared is again a constant. It is a constant multiple of the I. So as a constant multiple, it can be brought out in front of the sum, and then we have just the sum from 1 to n of I. And the formula for that is n times n minus 1 over 2. With this last term, again, the negative 64 over n cubed is constant in terms of the summation. And then we have the summation of I squared, the formula for which is n times n plus 1 times 2n plus 1 all over 6. Now, don't go hog wild with cross-simplifying because there's only so good it's going to get anyway, but we do have to move on and take the limit. The limit will take care of a lot of this for us without us having to go nuts with simplifying. But there are some basic things we should do, such as cross-simplifying those n's, or these n's, or this n with one of those. Beyond that, if you want to simplify the constants, you can. If it's easy enough to do so, go for it, but it's not a tremendously big deal. A lot of them will be taken care of when we do the limit. So we're left with just the constant 32 from that first term. In the second term, we have 32 times n minus 1 over 2n. And in the third term, we have 64 times n plus 1 times 2n plus 1 over 6n squared. Now again, thinking ahead a little bit, we will need to do the limit as n approaches infinity, and the second and third terms of this expression are rational expressions. So when we're doing the limit as n approaches infinity, it would help to have the numerators expanded, and because we're lucky enough to have monomial denominators, we can distribute the monomial denominators as well. So we're going to take another step or two here. 32 plus 32n over 2n minus 32 over 2n. In the numerator of the third term, we have these binomials to multiply together, and that should be familiar enough if you've done enough of these. It tends to come up an awful lot because it's the same two binomial expressions every time you have a sum of I squared. So the expansion for that, again, if you want to pause the video and work it through very quickly, the expansion for that is 2n squared plus 3n plus 1. So we have a negative 64 to distribute into that, and that gives us negative 128 n squared over 6n squared minus 192 n over 6n squared minus 64 over 6n squared. Now, the limit, we're ready to do the limit here. Oh, almost. We have a couple of simplifications that can happen here. Each of these terms has at least a factor of n in the top and in the bottom. Some of them, the n's cancel out entirely, which is very convenient and very helpful to us. At this point, it might make sense to simplify the 32 over 2 to 16. Now, I wouldn't, again, waste my time with simplifying the fractions that have a constant in the top and a power of n in the bottom. From experience, we should know that those fractions, when we take the limit as n approaches infinity, those fractions will approach 0. Um, 128 over 6 can be simplified to 64 over 3. That's about as good as that gets. Again, I wouldn't bother simplifying this because the limit will take care of it for us, and the same thing here. And at this point, we're ready to do the limit. So the limit as n approaches infinity of 32 plus 16 minus 32 over 2n minus 64 over 3 minus 192 over 6n minus 64 over 6n squared. The two important limit concepts here are that the limit of a constant is that constant, regardless of what the variable is approaching. It could be n approaching infinity, it could be n approaching a finite value like 0 or 5 or negative 8. It could be a different variable entirely, it doesn't matter. The limit of a constant is the constant. The other important property we have here is that the limit as n approaches infinity of a constant over a positive integer power of x, n approaches infinity of a constant over a power of x, that's not correct, a power of n clicked on the wrong thing. We'll let m be any integer, any positive integer power, actually any positive power. This limit is equal to 0. So that's exactly what we have going on here in many of these terms. We have these three terms which are constants, and then we have these three terms which are all constants over a power of n. Each of those will approach 0. So the whole thing becomes 32 plus 16 minus 64 over 3. So we can combine the 32 and the 16, but we're going to need a common denominator to deal with that negative 64 over 3. So before combining, I'm just going to handle the common denominator right here. 96 over 3 plus 48 over 3 minus 64 over 3. And no problem, feel free to use a calculator. And we get 80 over 3. And that is the value of the definite integral from negative 1 to 3, negative x squared plus 9 dx. A lot of work, certainly. We know that already, that Riemann sums are a lot of writing, a lot of algebra steps, simple algebra steps, but a lot of them. But one of the advantages of the definite integral, the first immediate advantage to us, is that it allows us to write the instructions for this problem to describe the situation in a much more compact form. In future lessons, the definite integral will serve further purpose for us, namely in something called the fundamental theorem of calculus, where we will find a faster way to evaluate a Riemann sum than using the Riemann sum. We'll use the definite integral instead. Did I not erase that? Oh, excuse me. That was from an old thing. I meant to remove that page. There we go. That's better. Okay, so properties of the definite integral. The definite integral has a number of things that we should be aware of because they do come up. Many of these properties are not something that we would describe a situation we wouldn't choose to create in many cases, but something that may occur naturally in the course of doing a problem or working through a proof. So let's start with the first and most basic of them. Oh, excuse me. We forgot the important clauses. Let f and g be continuous on a to b. So we've got some continuous functions there. Our first property is the definite integral from a to a of f of x dx. Now that is a little curious because the lower and upper limits of integration are both a. This actually corresponds to a region that has no width. Because remember, in the Riemann sum, delta x is the right endpoint of the interval minus the left endpoint of the interval over n. And anything minus itself is 0. So regardless of what the value of n, regardless of how many rectangles we would be using, whether it's a very few, very many, or approaching infinity, the width of the region is 0, and therefore the area is 0. A region with no width is one-dimensional, not two-dimensional. You cannot have a two-dimensional measurement of area on a one-dimensional figure, so the area is 0. That's an interesting one. Now, here's another very interesting thing to think about, something that none of the previous videos or examples shown in them have dealt with. But the fact is that area can be negative. And I know that sounds odd. Try not to think of it in terms of positive or negative, meaning greater than 0 or less than 0 as far as quantities go. Because when we are drawing the graph of a function, and we are looking at a region on it, we're doing so on the coordinate plane. And on the coordinate plane, negative doesn't mean less than 0, it means in the other direction. In the Riemann sum formula, the height of a rectangle is the output value of the function. Well, what if the output value of the function is negative? Then the area will be negative. Now that being said, there are two parts of the Riemann sum formula, and therefore two parts of the definite integral. F of x sub I, yes, but also delta x. Delta x could be negative. So f of x sub I could be negative if the output value is negative, but delta x could also be negative if we integrate not starting at the left and working towards the right, but starting at the right and working towards the left. Which is exactly what this next property deals with. What if, instead of the lower limit being a and the upper limit being b, what if the lower limit is b and the upper limit is a? What if we switch them? In that case, we would be integrating from right to left because the interval a to b defines b as being the right endpoint of the interval. So if we start at b and work our way towards a, then the delta x motion would have to be negative. The result then is that we will get, well, we're going to get the same value for area as if we did it from left to right, but because we're doing it from right to left, because we're reversing the direction, the sign of delta x changes to negative, and that causes the area of each of our rectangles to come out negative, and therefore the answer to come out negative. All the heights and widths would still be the same, but they would all have a negative value instead of a positive. So that is an interesting thing, that we can integrate in the opposite direction. And if we do, we get the same value, but with the opposite sign. This again is consistent with everything in the coordinate plane that suggests that on the coordinate plane, negative or positive simply indicates direction. Now, here's another very curious property. The definite integral from a to b of f of x is equivalent to the definite integral from a to c plus the definite integral from c to b. Now, again, why would you choose to split up an integral? To split up the interval? Well, there are actually some occasions where you may choose to do that. A piecewise function is a great example. It naturally has a break occurring. But that being said, this actually may come up for other reasons naturally, and it's not that we would necessarily start on the left and split it up into the two integrals on the right. We might end up with the two integrals on the right and have to combine them to get the one on the left. The point is that they are equivalent and we can do it in whichever direction is necessary for the problem we're looking at. Let's examine this one a little bit. Now, the most obvious kind of situation here would be, what if C is in between A and B? And I think it would help here because this is, we are talking about area, and this is geometrically based. So here we have some function, and we have an interval from a to b. And somewhere in between, we have this c value. Now, the region that we're interested in the integral on the left-hand side is from a to b. It's this section between those two dashed vertical lines. The suggestion here, then, is that what if we introduce another value in here that splits this into two separate regions? And we find the region area from A to C, and then separately from that, we find the area from C to B. Well, certainly, those two areas together should be equal to the full area from A to B. That should, I hope, go to some extent without really much discussion. We use that kind of thing in geometry classes when you have an irregular shape, such as something like this, where you're asked to find the area of it. And the trick to it is to split it into two nice regions, find the area of the nice regions, and then add them together. It's basically the same idea as the Riemann sum in general, finding the areas of the separate rectangles and then adding them together. Now again, would you choose to just arbitrarily split up a region like that? Probably not. It seems like a lot of work to take something could be done with a single integral and split it up into two, but there are times you might not have that choice, such as, if I may, an absolute value function. The absolute value function, at this point, we don't have a Riemann sum formula for it. There is no summation formula that would help us with the absolute value of x. And later on, when we talk about the fundamental theorem of calculus, we won't find any help there either. But what we can realize is that the absolute value function is actually a piecewise function. The absolute value function is a line with a slope of -1 on the left, and a line with a slope of +1 on the right. So what we get here is a naturally occurring split because the function has that corner point where it switches from, the transition point where it switches from one definition to the other. So what we've actually got is two separate functions defining the regions. Actually, because of the way the vertex of the graph actually sits on the axis, it actually splits into two completely separate triangles. But again, much like in geometry, what we could do is simply find the area of each triangle and add them. And that's exactly what we would do. We would go from -3 to 0 and integrate under the function -x. And then from 0 to 2, we would integrate under the function +x. And -x or +x, those we could do a Riemann sum for. Now, here's a curious situation which actually, again, will come up in the discussion of part of the fundamental theorem of calculus. What if C is not in between A and B? What if it is outside of it, to one side or the other? So suppose we have A and B, and the region between them is the one we're interested in. What if C is somewhere out over here? The integral from A to C would cover this whole thing, which is more than we actually are interested in. We only want from A to B. What we can do then is integrate from B to C and subtract it back out. So if we integrate from A to C, it's too much. And what we can do then is subtract out the integral from B to C. Now, this might not look exactly the same, but if you notice, compared to the expression up here, we have the opposite sign, and we're integrating in the opposite order. And that was one of the other properties we just discussed. So if we want to reverse the order of the direction of the integration here, we also would get to have the opposite sign area. Let me clean that up a little bit. That is a C, not an A. And so it does fit the property. Now again, why would you do that? Why would you integrate past where you want to go? Or if C was on the other side, why would you start before the region? Actually, again, that is something that may occur naturally in the course of doing a problem, and then we have to find a way to correct it, to deal with it. And that's where this property is going to come in handy. All right, there are two other properties which are actually very helpful in dealing with evaluating an a definite integral. And they should be familiar. We saw them with indefinite integrals and summation and limits and derivatives. They are the constant multiple rule, which says that the integral from a to b of c times f of x dx, much like we could do for limits, for derivatives, for antiderivatives, and for summation, we can bring that constant multiple out in front. Without going through a full proof for this, we can use a bit of logical reasoning to just kind of flesh out how we know this would work. C times f of x is a vertical distortion by a factor of c. So, for example, if c was, say, 3, it means that the y values of the function are 3 times what they were before. In terms of area and the Riemann sum, that means each height of the rectangles will be 3 times the height, and therefore 3 times the area. So literally, it's make the function 3 times bigger, then integrate, or integrate like normal and multiply by the 3 or whatever c might be afterward. If we needed to, we could sit here and go through the proof with the limit and the summation, but we know that c is a constant, and we know that it can be brought out in front of summation and out in front of a limit, so it would still work. The other one, which usually goes along with this, is the sum and difference rule. For, again, limits, derivatives, antiderivatives, and summation, we basically said that, hey, if we got multiple terms in our expression, that we can handle each one separately. We can do the limit of each term in the sum separately, or the derivative of each term in the sum separately. So if we have an integrand that is a sum or difference, we can integrate each one separately and then add them or subtract them. And again, this works both directions. If we find ourselves in a situation where we have the two separate functions being integrated over the same interval, we can combine it into a single integrand. That actually becomes relevant in one of the applications of definite integrals, and that is something we have to realize here is that we've been looking for the area between a graph of a function and the x-axis. Does it always have to be bound by the x-axis? What if it's between two functions? And it does work. Or in the case of the addition here, what we're basically getting is the output values of each function added together, which is the same as taking one rectangle whose height is defined by f and another rectangle whose height is defined by g, instead of finding them separately, stacking them on top of each other. Instead of a rectangle for f and separately a rectangle for g, what if we pick up the rectangles and stack them on top of each other? Or in this case, I'm going to, because of space, I'm going to slide it underneath. What if I slide it underneath there and make this distance f plus g? Then I can do it with a single rectangle instead of with multiple, separate rectangles for each function. And again, this can be used in either way. In the application I spoke of, finding area between curves, we actually start out with the two separate integrals and can combine them into the single definite integral. So definite integrals, right now, the new thing is the notation and the properties that go with them. In practice, as we saw with the previous example, the practice is that they still are being done with the Riemann sum to this point. We will reach a point in the next lesson where we learn the fundamental theorem of calculus and learn a much, much more efficient way to evaluate a definite integral.